of the second orientation lecture. We have also integral rules here. Integral of a constant function. It is, when you think of taking integral, it's actually the almost the opposite of the taking derivatives. When you take the integral of a constant, here we just have a c times x, and when you take the derivative of the x, it gives you the just c here. And since it's a definite integral, we have the limit points here, and we calculate it as just putting those values into the x here. It is the simply c times b minus b minus and c times a here. When you put the lower limit of the integral, you just multiply it by the minus here, and then by taking the common factor here, c times b minus a, and also we have the integral of polynomial functions. In this case, we have the function nth power of x, and we taking the integral of this function with the upper limits b and a, and the integral of this function is equal to n plus 1 power of x over n plus 1. In this case, we just increase the power of the function by 1, and then multiply it by the final power of the function, and then similarly we put those limit points to the term here. We put b here, and then we multiply by minus, and then we put a, and this is the common factor again as a denominator, and then we can the simplified version of the integral of this polynomial is this. And then we have the trigonometric functions. The integral of the sinus function is equal to minus cosinus x, and with the bounds, and it is equal to minus cosinus b for upper limit, and minus cosinus a, and the integral of cos x is equal to just sin x. In this part, we have additional minus sign here. In this part, we don't need to change the sign of the function. It's just equal to sin x, and for the limit points, it's equal to sin b minus sin a. And we have the tangent function here. The integral of the tangent function is x equal to minus natural logarithm of cos x. It actually is equal to, when you take the derivative of this term, is equal to the sin x over cos x, which is equal to tangent x. When you take the derivative, you will see, and it is equal to minus ln cos b plus ln cos a. There is a minus sign here, therefore this turns out to be plus, and then we have cotangent function. It's very similar approach here. There is a similar approach here. It's actually equal to ln sin x here, and then for the bounds, it's equal to ln sin b, and it has to be negative. It has to be minus ln sin a here, and then we have the integral of power functions. The integral of power functions, as you know from the derivatives. When you take the derivative of a power function, which basis is equal to e is itself, and therefore the integral of x power of e is also equal to itself. For the bounds, for the limits, upper and lower, it's equal to b power e minus ea here. And then we have the integral of 1 over x. And when we take the integral of 1 over x, it gives you 2 ln x. And you may remember that when you take the derivative of ln x, it gives you to 1 over x here. And for the bounds, it is equal to ln b minus ln a. And then we have the power of a constant here, which is x power of c, and it is equal to x power of c itself, and it's divided by the ln c, which is the base of the power function. And when you put those limit points, you get the following equality here. And for those, we have examples. In the first example, we have a constant function here, which is equal to 2, and we need to take the integral of this function for the upper bound for lower limits of 1. As we mentioned about this, when you take the integral of a constant function, it gives you 2 times x, and for these limit points, it simply gives you 2 times 4 minus 2 times 1. We just put those values to our function, which is we already take the integral, and it is equal to 6 here. And then we have second integral here. It's a polynomial integral, and it's when we take the integral of polynomial function, its power is increased by 1, and it's become third power of x, and then we divide the function by its final power, and then we just put those limit points to the function, and then we get 63 here. And then we have another polynomial function is here, and there is an additional coefficient case. We just take the integral of the polynomial function, and then we just multiply it by the coefficient. The integral of this function is equal to 5th power of x, and it is divided by 5, and then we just multiply it by the coefficient, which is minus 3, and then we just put those lower and upper limits to the function. We get minus 3 times 32 over 5 minus 0 over 5, and it gives you to minus 96 over 5. In this case, we have multiple polynomial functions and a constant. When you take the integral of these functions, you can just use the linearity, or you can just calculate the integral of those functions and constant function together. But you can think of it partially. First of all, we need to calculate the first polynomial function, which is its integral is equal to 4th power of x over 4, and then we pass to the second one. The integral of it is the 3rd power of x over 3. We have a coefficient here, minus 1, and we multiply it by the minus, and then the constant function of 4, and it gives you 4x here, and then we put those boundary points to the function here. For 3, it's just fourth power of 3 over 4, which is equal to 81 power over 4, minus third power of 3, which is equal to 27 over 3, and 4 times 3, which is equal to 12, and minus for the lower limit, we just put those minus 1 to the axis here. The fourth power of minus 1 is equal to plus 1. We have a denominator here, therefore it is 1 over 4, minus, when we put minus 1 to the here, it gives you 1 minus 1 over 3, and then we put a minus 1 here, we get minus 4, and finally we get a value of 36 minus 26 over 3. In this example, we have trigonometric functions, multiple trigonometric functions. We have 3 sin x minus cos x. We know that the integral of sinus x is equal to minus cos x, and also we have a coefficient here, therefore we multiply it by this, and then we have cos x. The integral of cos x is equal to sin x. We don't change the sign of the function, then we take the integral, and then it becomes minus 3 times cos x minus sin x, and we have the values for the trigonometric functions, and we have p here and p over 2. As you may remember from the previous courses or lectures, p was equal to 180, and the half of this is equal to 90 here. When you put those values into the trigonometric functions, it comes cos p and sin p, and for the lower limit, we have the p over 2, and from trigonometry courses, it was equal to, the cos p is equal to minus 1. Therefore, it comes positive 3, and then we have sinus p here, which is equal to 0, therefore it's minus 0. And then for the lower limit, we have the cos 90 degree, which is equal to 0, and we have the sinus 90 degree, which is equal to minus 1, just 1, and we have a minus here, therefore it becomes minus 1. And finally, when we sum them up, and simplify it, it's become 4. In the another example, we have both trigonometric function and polynomial function. We're taking the integral apart. When we take the integral of sinus x, we already know that minus cos x, and when we take the integral of this polynomial function, since its power is equal to 2, it's become 3, and we divide it by the 3, and then for the limit points, it's become minus 2 times cos p plus 3 third power of p over 3 minus 2 times cos 0 and minus 0. From the trigonometry, the value of the cos 0 is 1, and the value of the cos p is equal to minus 1. Therefore, when we multiply minus 2 by minus 1, it's become positive 2, and then we have third power of p over 3, and then in the right hand side we have the minus 2. The minuses are cancel out each other and become plus, and finally we have 4 plus third power of p over 3 here, And example 7, we have a different functions, which is 2 over x plus 3 times x power of e. We need to take the derivative of it. From the fourth rule, we already mentioned about previously, the integral of 1 over x is just simply natural logarithm of x, and we have coefficient 2, it's become 2 times natural logarithm of x. And we know that the integral of ex is equal itself. Therefore, with the coefficient, it's become 3 times ex. And for the limit points, it's just comes 2 times natural logarithm of 3 plus 3 times third power of e minus third 3 times e here. And also for the properties for integral, we have some additional examples. Those are for the properties. And for the first probability, which says if the limit points are equal to each other, then the integral of the result of this integral becomes 0. There is no need to calculate those values when the limit points are equal to is equal, and we can just simply say it is equal to 0. And then we have the second example related to the second property. It was saying that we can change the borders, limit points. We can reverse those values by changing the lower bound 2 with 1, and 1 become the lower bound, and changing it the plus sign with the minus sign. And then if we change the value of this with the reversed limits version, it becomes the positive plus the integral and the minus 1 of the integral. Since they are exactly equal to each other, we can just simply say that they are cancel each other. It becomes 0. In this example, we use the fourth property. In this property, it was saying that when the functions are equal to each other, in here we have the same functions, and when the upper limit of the first integral is same as the lower limit of the second integral, we can just simply write it like this, just starting the limits from the 1 and finish it from 3, and the 1 becomes the lower limit and 3 becomes the upper limit here, and then we just use the same function here and just taking the 1 by just calculating this limit, this integral, we can get rid of calculating 2 integral here. And when we calculate the integral of the third power of x, as we know that, it is the fourth power of x over 4, and the boundary points are 3 and 1, and it becomes h1 over 4 minus 1 over 4, and it is actually equal to 20. And in here, we have the third property from the linearity. We can actually add those functions to the another integrals inside. if the boundary points, the limit points are the equal, and when we do this, we can see that it is clear. There is a positive second power of x and a negative sign of the second power of x. When we add them up, these terms are cancelled each other, and then we come up with third power of x plus 1. So there is no need to calculate the integrals of the second power of x terms here. We can just calculate two terms here, and we have the limit points 4 and 2, and then when we calculate it, it is equal to 62. For the fifth example, in order to apply or use the fifth property, which is when your function is even and the boundary points are the same, but the lower or the upper limit points are the reverse signed, we can just use the 0 and the upper limit here. And since fourth power of x and the second power of x are both even functions, the summation of those functions is also creates a even function. So there is no need to calculate to -2 here, because the 0 is easing our work for estimation the integral. When we take the integrals of those polynomial functions, we get fifth power of x over 5, and then third power of x over 3. And since they are even, and we change the limits, and we double the integral, and then when those points, for 2, we get these values, and for the 0, it's got 0. It's making easier our calculations, and then we just sum them up, and then just multiply it by 2, and we get 272 over 15 here. This is the end of the integrals and derivatives, and then we pass to the linear algebra. And okay. First, we need to talk about the vector spaces, and then I will pass to the matrices. Linear algebra is the study of linear maps on finite dimensional vector spaces. Therefore, we will start with the vector spaces, which is a set whose elements are vectors. The vector space in two-dimensional real space, which is, we can think of a plane. It's two-dimensional, consists of all ordered pairs of real numbers as follows. Pairs here is a pair of two elements. We have a vector with two elements here. X and Y are the elements of the real numbers, and these pair is in the 2D real space. And also we have the 3D space, which is the ordinal space for us. And in this one, we have three elements, X, Y, and Z. Each one is in the real number space, and those creates the 3D space, which is R3. We can increase the dimensionality of the vector by just adding some elements in the vector. The linear combination between the vectors is easy. We can add the two vectors. In our cases, it is a V and it has two elements, V1 and V2. And then we have the second vector. It also have two elements, U1 and U2. When we add those vectors, we get V1 plus U1, and the second element of this vector addition, V2 plus U2 here. And also we can subtract the vectors as well. When we subtract the V1, U1 from the V1, we get V1 minus U1, V2 minus U2. And also we have the scalar multiplication for the vectors. If you want to double a vector, you can multiply the vector by 2. It's actually an ordinary multiplication, but in this time we have two elements. Actually, we have a vector. When we multiply a vector by a constant, we need to just multiply by the vector's elements, each of the elements by the constant. So we have the 2W1 and 2U2. And also we can make it negative by multiplying by -1, and we get minus VU and minus VE2. And also we have linear combination, which is we can sum them up or subtract with the coefficients, and we get a desired result here. For this, we have an example. Let's say V is equal to 1, 0, and 3, and then we have U, 1, 2, and 3, and we have the W, 2, 3, and -1. When we make the calculations for this rule, the linear combination, we just need to U itself, and then the 4 times V, and -2 times W, just multiply by the vectors with the coefficients. In this case, there is just 1, and there's no need to multiply it. And then we have 4 here. We need to multiply each element of the vector by 4, and we get 4, 8, and 12. And when we multiply the third vector with -2, we get -4, -6, and 2. And we can just sum them up, and we get finally 1, 2, and 9 here. And we have also dot product for multiplying the vectors, not with scalar or a constant. We are multiplying the two vectors here. We call it dot product or inner product. For this, we already know that U was U1 and U2. In each, the elements of the U vector was U1 and U2, and the elements of the W was W1 and W2. We just multiply the first elements of the vectors each other, and then we sum them up with the multiplication of the second elements of the vectors. In this example, we have 4 and 2 in the first vector, and the second vector we have -1 and 2. And we want to estimate the dot product of these vectors. We just need to multiply the first elements of the vectors, which is 4 and -1. And we multiply it, we get -4, and plus multiply 2 by 2, and we get 4, and and as a result, we get 0 here. And then we pass to the matrices. We can start with two equation here, which are consist of two variables, x and y, and they have coefficients. If there is no coefficients in front of an variable, we can say that its coefficient is 1. And also we can write this equation system as a matrix equation system. For this, we just need the coefficients of the equations and the variables and the equalities. The coefficient of x here is 1, and the coefficient of y is -2 in the first equation, and the second ones are 3 and the 2. So we have the two variables, x and y, therefore we multiply by the x and y. This is the variable matrix here, and which is equal to 1 and 11 here. In here, in the system of a times x equal to b system, we call the a part, which is the first part of the system. We call it coefficient matrix. It corresponds to the coefficients of the variables in the equation system or matrix equation system. And then we have the description for this matrices. If we assume the matrix A, we can say that it's a 2 by 2 matrix here because it has two rows, and two columns here. Therefore, we say that it's a 2 by 2 or 2 times 2 matrix here. For this B matrix, we can say that since it is a 2 rows and just 1 column, we can say that it's a 2 by 1 matrix here. And it can be written as 2 times 2. And also we have matrix multiplication. For this, we consider two matrices, and we want to multiply those matrices each other. And we assuming that when we multiply those A and B matrices, it gives you the C matrix, which is the elements of the elements are seen like this. And we can also talk about the elements here. In this situation, we have a 3 times 3 matrix, and also B is a 3 times 3 matrix as well. This is the element of A matrices, which is in the first row and the first column. And also we have another element here, which is in the first row and the third column. These numbers are corresponding for the place of the element in the matrix system. Okay, so then we turn back to the multiplication. We have A matrix, A and B matrix. And then we multiply them. It gives us to the C matrix, and these are the elements of it. And for this, we have a formula here. When we want to calculate the each row and the jth column of the C matrix, we just can calculate the element as this formula here. it is the summation symbol here. It is actually can be understandable in the following example, but we just using this order here. In this case, we have, in this example, we have 2 by 2 example. The first matrix consists of 2, 1, 3, and -1. In B, we have 0, -1, 2, and 2. In this case, the A11 element is 2, A22 element is -1, and this is the A21 element. It is in the second row and the first column, therefore we call it A21. And similarly, if you want to calculate the multiplication of A and B, we assume that they are equal to the multiplication of A and B is equal to matrix C. In this case, since our matrices are 2 by 2, we get a 2 by 2 matrix here, which is C matrix, and the first element of the C matrix is E11. We just want to calculate the first row and the first column of the matrix here. We just put those values into the E and J in this part. Then we just put those values. E is equal to 1. We just need to put here 1, and then J is equal to 1. Just need to put here 1, and then we ended up with the only term here is K. The only changing parameter is here K, and it goes to N in our case, since it is a 2 by 2 matrix, it is 2 here. And then the value of K is equal to 1. We need to calculate A11 times E11. And then plus, since it's a summation symbol, we need to sum those values for different K values. And we already said that N is equal to 2 in our cases, because those are 2 by 2 matrices. K in this term is equal to 2. Therefore, we need to put 2 to the K values, and then we get plus A12 and B21. And then it is easy. We know that A11 was 2. Therefore, we put here the 2 value, and then we have the B11. We pass to the B matrix, and it's its 11 value is 0, and then we put here 0 plus. We pass to the second term here. A12, it is in the first row and the second column, therefore it is 2. It's 1, and the second row and first column's value of the B is equal to 2. Therefore, we multiply it 2, and finally it's equal to 2. We found that the first element, I mean the 1 element of the matrix, is equal to 2 here. Similarly, we can just changing the E and J values, I and J's values by the corresponding numbers. We get the similar calculations, and then we calculate those summations for the 4 elements of the C matrices, and then finally we get the A times B, which is C matrices, and it is equal to 2, the 1 element of the matrix, which is equal to 2, and then we have the second, which is equal to 0, and then -2, -5. And we need to talk about the identity matrix before taking the inverse of a matrix here. Identity matrix is just a matrix that it's a square matrix. If its size is n, then it has to be n by n matrix, and which is a square matrix with ones on the main diagonal. Diagonal means in the matrix is these values. These values are the diagonal values. They has to be equal to 1. All of them has to be equal to 1. And the rest of the elements else where in the diagonal matrix has to be equal to 0. The diagonal values of the matrix has to be 1. All of them has to be 1. And the rest of the matrix values has to be equal to 0. It could be 2 by 2. Just this area creates the 2 by 2 identity matrix. This area creates the 3 by 3 matrices here. And this is the n time n matrix, identity matrix here. We denote it as a capital I here. It's corresponding for the identity matrix. It actually similar to the multiplication operator one. Okay. Then we'll pass to the inverse of the matrix. Then we want to take two matrices here. We just need to calculate this formula here. Let's assume that we have an A matrix here, which contains the elements A, B, and C, and D. For taking the inverse of A, first we need to calculate this ratio here, which is 1 over A times D minus B times C. We just using those elements in the square matrix. And also we multiply it by the D minus B and minus C and A. In here, A and D values are changing their positions in the matrix, and the rest of the values take the minus. We just multiply those values by the minus, and then finally we get the inverse of the matrix. In some cases, we need to calculate the inverse of a matrix. In such a case, like A times B equal to C, if you want to find the elements of the B, you just need to find the inverse of the A, because in this equality, we have additional A. We cannot just simply divide C by A. Therefore, we need to find the inverse of an A. In this case, in linear algebra calculations, in order to get rid of the A matrix here from the left-hand side of the equality, we just need to multiply this left-hand side and right-hand side by inverse of an A from the left. If we multiply by this A from the left-hand side, it creates an identity matrix, and which is for 2 by 2 case is 1, 0, and 0, 1. Then we multiply by the equality here. We get an identity matrix here, and we get rid of the A here, and then just simply say that B is equal to inverse of A times C. Okay. By calculating this multiplication, we can calculate the B here. For this, we have an example. Let's say we have a matrix A, the elements of 4, 7, 2, and 6. So by just calculating this formula here, we can calculate the inverse of the A. We know that the formula starts with 1 over A times D minus B times C. A was 4 and the D was 6. Therefore, 4 times 6 minus this element and this element. And then we just need to change the positions of the diagonal values in here, or change the position with the 6, and then we get 6 and 4, and then we just multiply the other elements by -1, and we get this matrices here. And then by calculating this, we get 1 over 10 times the matrix. This is the inverse of the matrix, and then in this case, by just multiplying the C, we get the B matrix here. The next examples are written in text, written with hand. Okay, let's zoom out. For the first example, we have a huge matrix here, 4 by 5 matrix here. And in this example, I will also talk about the row reduced echelon form. What is it? Row reduced echelon form. And also I will talk about here the matrix operations. And also this say elementary row operations. Okay. Actually, our aim is here to find a version of matches that creates the leading values of 1 in the columns, and the columns other than 1, the values other than the 1 has to be 0 in the columns. As you can see here, there is only one in this column and in this column. And then we want to create a triangular here. And the last column, last row can be consist of zeros. It doesn't matter. But the leading ones has to be the other values has to be 0 here. The rest is not necessarily different than has to be 0. We're just looking at those values just for the leading values. We want to transform the starting matrix, the beginning of the matrix, to this version. For this, we just start with, in this case, changing the rows of the first and the third rows. We want to just changing the places of the first and the third rows. We carry the third row to the first place, and carry the first row to the third place here. This is the appropriate notation for replacing those rows in our matrices. Just changing those rows. And then in here, we just divide the second row by 2, first row by 2, and write these values to the first row. As you can see, when you divide the first row by 2, it becomes 1, it becomes also 1, it's -5 over 2, it's become 1, it's become 2, and we have a leading value here, but the 2 value is has to be 0 here. Therefore, we just subtract the -2 coefficient of the, multiply the first row by the -2, and then sum with the fourth row, and then write it to the fourth row here, and hence, and final, and finally, we make this 2 value 0. Therefore, we create a first leading value as 1, and then we need to pass to the second place. There, in order to do that, we just changing the second and the fourth rows places, and then we just multiply the second row by the -1/2, and it makes the leading value 1, and then we subtract the second row from the first row, then, and by doing it, we just making the second value of the first row 0, and then we just subtracting to the -2 times second row from the third row, and we get this matrix here, and then it makes this value 0, and then we pass to the other rows in the matrices, and doing these operations, we create step by step the row reduced echelon form of our matrices. And we have the second example here. We have a matrix B, which is equal to 1, 2, 1, -2, -3, 1, and 3, 5, 0. And we want to find a row reduced echelon form again. In order to do that, we multiply the first row with the 2, and then we just add it to the second row in order to get a 0, because we want to make the other values other than the leading value 0, and then we subtract the third power of the first row from the third row, and we make the value of 3 0, and then we add the second row to the third row in order to make the -1 here 0, and and the final operation, we get the desired result here, the row reduced echelon form of a matrix. And also we have another example for the taking the inverse of a matrix. In this case, our matrix is here A, and we see the elements of the matrix. This is the second way of estimating the inverse of a matrix here. We just take the A matrix here, and then we write the identity matrix that carries the same form of our original matrix. This is the 3 by 3 matrix here, and therefore we need to put an identity matrix that carries the form of 3 by 3. As we mentioned about that previously, the diagonal values of the matrix has to be 1, and the others has to be 0. And then our aim is here to obtain an identity matrix in here by using the matrix operations. We just want to, in the above examples, we use the matrix operations in order to get and reduce row reduced echelon form, we use the same operations for making this part equal to this part. For that, we subtract the second 2 times of the first row from the second row, and we get 0, -1, -1, and then we subtract the 3 times R1 from the row 3, and then we get 0, -4, and -2 here. We already get the first zeros in our first column. We step by step approaching to the identity matrix here. After that, we just add the second row to the first row in order to make those values 0, which is seen as here. And then we subtract the second row, 4 times second row from the third row. We make this value 0 and make this value 2. We already make the values, those values 0 and 0, 0, 0. And then we need to make this value as 1. This value has to be 1. This one has to be 1. Pardon. This value has to be 0. And then just multiplying the second row with the minus, and then we just divide the third row with the 2, and then we get 1, 0, 0, 0, -1, 1, 0, 0, 1. We are very close to the identity matrix here, but there is a problem that we need to get rid of this. So for this reason, we need to subtract the third row from the second row. Therefore, we make it 0. And then finally, when we do the other operations, we get the identity matrix in here and the inverse of the matrix in here. This is the final form of inverse of our matrix A. This is the second way of finding inverse of an matrix. Thank you for listening. This is our end of our orientation lectures.